Swayam Prabha. Digital India. Educated India.
Now, what we would start henceforth is an area known as so this lecture would be mostly a storytelling session. So, where I would describe things, set up things with a few problems thrown in here and there, and then possibly in the afternoon class we will see some examples of it. Okay. Now, think of the following situation. You have a network router. Think of the traffic going through it. So, what does the network router do? Gets a packet, checks its destination address where it has to go, sends it. Now, this network, this router is a small computing device, right, which has very less amount of space with it, but the data that is going through it is huge, right. Now, say for example, this network company wants to do something with the network traffic that has gone through this router throughout the day. Say for example, it just wants to figure out how many distinct IDs were there. Right. So, each one has a address imprinted on it. So, it just wants to figure out how many distinct addresses to which I have sent the data. You appreciate the problem? Now, think of this problem in your RAM model. What is your RAM model? There is a kind of a monolithic memory whose any location can be accessed in order one time. That is a RAM model for you, and each data kind of fits into the width of this. So, 1 unit is the integer that you are going to handle. So, it is kind of the word RAM model. So, your problem is as follows. So, you have an array say having these elements A1, A2, AN, and your question is find the distinct elements, or the number of distinct elements. What do you do in your usual RAM model to find out the distinct elements? Hmm? How do you delete duplicates? How do you find duplicates? So what time would you take? N square. Okay. So her algorithm is, you look at the first element, run through the array to figure out if there are multiple instances of this, right. So what you do is you take linear time for each element. So for the first you take n, for the next you take n minus 1, so on and so forth. If you look at the sum, it is proportional to n square. Can we do better? Hash. Hash is a very precious weapon. Don't use it here and there. There is a saying. I am a Bengali. There is a saying in Bengali which translated to English is roughly like this: shooting cannonballs for mosquitoes. Yeah. So hash is like a very precious weapon. Don't throw it here and there. So I think Venkatesh will have a lecture on hashing tomorrow, and then we will show you uses of hashing. Hash, you can hash obviously, but there are particular situations where you hash, otherwise it becomes too costly. Yeah. So apart from hashing, any other answers? I want to do better than n square. Good. If you sort the element and then just run through. So if you sort the element, if there are multiple instances of the number, they will be consecutive side by side. Whenever you have a border, you know that one distinct element is gone, right. So in RAM you can do it in n log n. Can you do even better? Now see, this area of algorithms is about, algorithms would always talk of efficiency, of doing better, still better, still better. But is there a limit beyond which you cannot get better? That is the notion of lower bounds, which we will also do. So say for example, if you look at sorting, right. Now by now you know some n log n algorithms for sorting. If you look at your fast sorting algorithm of bubble sort, by the way that is my favorite sorting algorithm, bubble sort, you just bubble up n square time, nice algorithm, right. But you are not happy, so you wanted to do even better, you landed up with n log n, your heap sort, mart sort. Quick sort in the worst case is not n log n, but in the average case it is n log n. Then again people brought in randomization. In randomization also you saw that expected case was n log n, quick sort. Next question is, can you do sorting better than n log n? If you can do sorting better than n log n, then this distinct elements is also solvable in better than n log n. So can you do, have you ever heard of a sorting algorithm that outperforms n log n? Have you not heard? Linear time sorting? Not studied? Not studied things like counting sort, bucket sort? Huh? None of you have heard of this terms? Okay. There are sorting algorithms which sorts in linear time, but there are assumptions on the input, right. So you have assumptions like the numbers come within a range, then you can have assumptions like they are uniformly distributed in certain range, but without those assumptions on the input, if your numbers are arbitrary, then n log n is a lower bound. One can prove it. The idea for proving such a lower bound is, I am not going to the exact proof, but see, when you talk of lower bounds, so say there is this problem of sorting. Mind you, all these sorting algorithms that you kind of looked at, bubble sort, selection sort, merge sort, quick sort, heap sort, they are all comparison based sorts. That means the machine in which you sort has the power to compare two numbers and tell you that this is greater, this is less. So, this is my machine. So, the moment you want to solve a problem, what becomes very crucial is the machine in which you are solving the problem. Look into this distinct elements problem. It is pretty easy to solve this when you are in the RAM model, right. It is just a no brainer almost. You sort, you are done. But think of the same problem on this network router model. You have probably 1 million, 10 million packets going through this router in a day, and if you want to apply this algorithm, then you have to sort. How do you sort? Because what is the router doing? The packet comes, sees the destination ID, sends it. Until and unless the router has enough space to hold all of these IDs, there is no way that this router can figure out the number of distinct elements. See, the same problem, when I take it from this RAM model to a different model of computation, it becomes extremely difficult, right. So, you appreciate this one, you appreciate this fact that if I change the machine model under which I compute, the difficulty levels of problems change and change dramatically. So, I will give you a machine model very soon, which is actually the streaming, which basically models this kind of network traffic computation. But before I get into that, let us talk a little bit of lower bounds. Now, see this fact that the moment you have started appreciating this fact that, well, this distinct element problem is no longer very amenable in this new machine model of router computation by the router, then you start thinking, well, there might be even impossibility results, right. An algorithm is kind of a possibility result. When you solve this distinct element problem in your RAM model, you showed that it is possible to solve this problem under the RAM model, right. So, it is I have given you a nice algorithm as a proof of the possibility of the fact that this problem can be solved. So, an algorithm is a proof of a possibility, but when I change this model for the same distinct element problem to another model, hey, it seems not possible. So that means, can there be impossibility results? Meaning thereby that we saw that for these distinct elements, if this network router was allowed to store everything, it could have solved it. So, the impossibility result might be something like this, that until and unless you allow me to store everything, I cannot solve this problem, right. So, this impossibility results a kind of this lower bounds. Now, let us come back to the sorting problem. Under this RAM mod, and let us even make this machine model more rudimentary. So, I give the machine the power to compute, rather to compare two numbers, right. So, that is why it is comparison based sort. Now, if you look at your quick sort, your bubble sort, your selection sort, whatever, essentially you compare, right. You compare, and based on the comparison you do something, either you swap or you allow it to remain as it is. So, that is the reason your number of swaps are never exceeds your number of comparisons. So, you measure the number of comparisons asymptotically and you think you are done, fine. Now, coming back to this, so I need to model a machine which kind of has the power to compare. So, the way these lower bounds are proved is as follows. So, you have this comparison based sort. So, you have algorithms for it, say maybe quick sort, heap sort, my favorite bubble sort, merge sort, so on and so forth. These are algorithms to solve a problem. So, now you have a problem, a well posed, well defined problem, and a machine model on which you solve this problem. Now, think of the sorting problem and the relevant machine for it. What it can do is it can compare say two numbers, x1, x2. So, in sorting what do you have? You have n numbers and you compare and then do certain things. So, so you sort. So, based on x1 less than x2, rather let me write it this way. To make our life simpler, let us think of these numbers to be distinct. So, I first check whether x1 is greater than x2. If yes, I do something, if no, I do something. Again at a stage I compare two numbers, I keep doing, right. So, look at your favorite sorting algorithm and you can model it in this fashion, right. So, for example, bubble sort, you compare x1 with x2, whichever is greater, then you compare x1 with x3. So, somewhere down the line in another of the nodes of the tree, those comparisons will come, and this tree kind of grows. Now, you will have leaves of this tree. So, what are the leaves? When you need nothing to do, that means you have got a sorted output. Now, mind you, a sorted output is any one of the factorial n permutations of the number that you are given. I have made all of the numbers distinct, so that you have factorial n permutations, fine. So, my leaves are any one of these factorial n permutations. So, that means my machine model is such that it starts from a location, from the root, makes comparisons and find its way to any one of these permutations, which is a sorted order. Now, what is this? What does this height represent? The number of comparisons that you did. And mind you, for a tree, if you are on a leaf, there is a unique path. There exists a unique path from the root to that leaf, right. So, given your input sequence, there is a unique sequence of comparisons that leads you to your final sorted output. So, now you know the relation between the height of a tree and the number of leaves, right. So, now the point is, you can now put a bound on this height to argue about a lower bound on sorting. So, it is simple. If 2 to the power of h is the say minimum height, and take log on both sides, and you can figure out that h is n log n. So, that is the idea. Now, mind you, in here the lower bound that I was giving you was a lower bound on the number of comparisons that you make, and the complexity that we were analyzing was the time complexity, right. So, we at some point we said that the time complexity is proportional to the number of comparisons that you make, right. So, this n log n is kind of a lower bound on the time complexity of a sorting algorithm, where there is no restriction on the input of the sorting. Mind you, that if there are restricted inputs coming from particular domains, one can even go less than n log n. There are sorting algorithms known as counting sort, bucket sort. There this hashing idea is used in some way. So, but again, as I said, there are enough assumptions and restrictions on the input. So, I have given you an idea of lower bound on the time, but if you now look into this network router problem, the impossibility, so this is kind of an impossibility result, right, that you cannot sort in time less than n log n. So, similarly in the router problem, what was the impossibility that we saw? That until and unless you are storing the entire traffic, nothing significant can be done. So, that impossibility result translates to a lower bound on space. So, we need ideas to prove lower bound on space. So, for streaming algorithms impossibility, we would need ideas to prove lower bound on space. Fine. So, I have given you notions of impossibility results and lower bounds. Let us now enough of storytelling, let us now get a bit more concrete. Let us now define this model. What is this model? That is one characteristic, surely it is large. This is very important. So, I call this to be the string. So, I will call each AI to be a token. Okay, what did I write? Now, see, in when I was looking into this RAM model, I could access data in any way I liked. There was no sequence, but here I am imposing a sequence. What does that mean? That you can only see the data in this direction. First you see A1, then A2, then A3, so on and so forth, AN. That is how your router behaves. Fine. Okay. So, the length of the stream is M, and each element in this string takes a value between 1 to n. That is the universe in which each token belongs. Fine. Okay. Now, reading this data in the sequence actually makes your life very difficult. So, once you have seen A2, you cannot see A1 any further. That packet is gone. Okay. So, what you can do? So, there is this notion of pass. P on probabilities. So, there are multipass algorithms where, now see, multipass means in first pass you read the data as A1, A2, AI, AM. In the second pass also you have to read the data in the same sequence. You cannot alter the sequence. Ideally, we would talk of single pass algorithms. Okay. So, what is just the extra thing that I have? So, you can use some extra space. And obviously, sublinear, because if I allow you linear space, you will store the entire data, right. If the router is allowed linear space, it will store everything and then it can compute anything. So, the holy grail is sublinear space. Ideally, Why log n plus log m, or minimum over log n log m? Because see, your universe is of size n. So, to encode each token in binary you need log n bits. You appreciate this? Because to write the number 0 to 7 you need 3 bits, right? This binary representation all of you know, right? So, to count the number of elements in this stream, in a counter I need log m bits, because the stream length can be m. If I need a counter to store how many elements gone past, then I would need a log m bit counter, and to encode each element of the universe I would need log n bits. So, my goal would be to solve these problems in space log n plus log m. But as one would show you that it is not always possible, again then impossibility results would come, and then people get up to say square root n, but again the main goal is to remain sublinear strictly. So, that means it is small o of n. Okay. So, Venkatesh has already done this Mishra-Grice algorithm for you, right, estimating the frequency. Let us look at, I think this he has not done, let us look at a problem like this. You understand this problem? So, my input stream is say for example, if I am looking at the numbers this, so my input stream could be 5, 3, 1, 2. Right? So, one element missing, you have to find that. What n into n plus 1 by 2? You have a write a equation from 1 to n. See, in RAM model again it is very easy, right? What do you do?
Calculate the sum and subtract it from sum of n plus 1.
Okay, that is a nice idea, but how do I do it in streaming? Okay, I take forward his idea. What I do is, so I have been told that my stream is say sum A1, A2 distinct an minus 1 and sigma is comes from a permutation of n. So, the first element comes, what do I do? What do I do now? Yeah, go ahead. You had a nice idea. Go ahead. Add every element. Okay. So, his idea is as follows: declare a sum variable. So, that means it is a space. Huh? So, you add this. In the next step, make sum equals to sum plus A2, go on. Fine. So, the sum is growing in size, right? A1 plus A2 plus, what would be the size that you need for the space that stores this value sum? Linear space, why? Can I put a bound on this value of sum? Sum of these elements, right? It cannot get more than, right? Which is big O of n square, right? To represent a number n, how many bits do I need? Log n. To represent a number n square, how many bits do I need? Right? Order log n. So, to represent any number that is poly in n, I require order log n, right? You agree to this? So, what I do? My extra space is log n and I am happy with that. So, I store the sum, at the end I subtract it from n into n plus 1 by 2, then I have found the missing element. Okay. Now, I change the problem a little bit. How would I change? Instead of 1, make it 2. What do you do? Does your idea still work? What do I do? Declare a binary array with true or false. Binary array of what size?
Take an array with
Huh?
you will take another array, sir.
Another array. I have not taken an array, it was just a log n bit counter. So, the idea is not very far from what you did earlier. see I have two variables that I need to fix. So, that means I need two equations to solve them. One comes from here, the other comes, what I do is, right, I square and keep this sum, and I know the sum of 1 square plus 2 square plus up to n square, subtract it. Still you can do it in log n time, right? Did you get the idea? Yeah, okay. Now, you understand that things would start getting difficult. Now, let us formalize a few things. One is we would start talking in terms of the quality of the solution. Professor, this class goes up to 12:45. So, quality of the solution. So, what I have is a stream phi. Now, see this distinct elements problem that I gave you in the streaming model, I cannot exactly solve it, right, but there may be an approximate solution, right. So, what I do is first I define so, say for example, in this problem of finding missing element, what were you throwing out? The sum, right. So, for distinct elements you have a number, that this is the number of distinct elements. We will see many other problems, but for any problem I can abstract it out as that given the stream I will give you a number as an answer, fine. Number of distinct elements, approximate counting again a number, frequency moments we will see again a number. So, I see that the output that this algorithm, streaming algorithm would give is a real valued function phi, fine. So, phi takes sigma gives you a real value. A is say your streaming algorithm. So, as I have seen that the streaming algorithm throws out this value. Now, for many of the cases this streaming algorithm would not be able to solve the problem exactly, it will only solve it approximately. So, we will look into this distinct elements problem and give you an approximate solution. Now, what is a good approximate solution? You should be, your output A sigma should be as close as possible to this phi sigma, right. So, we would now define a notion called an epsilon delta algorithm. Where epsilon is an error parameter and delta is a probability measure. Most of the cases, this Mishra-Grice algorithm that you saw was a deterministic streaming algorithm, this finding missing elements was another deterministic algorithm, but most of the streaming algorithms would be a probabilistic algorithm, would be a randomized algorithm. Because without randomization you would see that almost you would be able to do nothing. So, make a comment that for most of the cases this would be a randomized streaming algorithm. So, this is the error.